Hi, I'm Lexi, and I'll be going over the module for practice problems. So for our first problem, we have our random sample of 90 adults is classified according to gender and the number of hours of television watched during a week. And so we have our little table over here, and using a 0.01 level of significance, we want to test the hypothesis that the time spent watching television is independent of whether the viewer is male or female. So to do this, we want to use the chi-square test of independence. And so first we need to write our hypotheses. So we have our null hypothesis. So this is going to be time spent watching TV is independent of gender. And then our alternate hypothesis is the opposite. So this is time spent watching TV is dependent on gender. So we have our hypotheses, and then we can write down our alpha value. And now we can calculate our expected values. So we see the formula for expected values is right here. So that's where we basically get our counts for our columns and rows, and we multiply them and then divide them by the total count. So first let's write out our counts for the rows. So we have 15 plus 27. So this means our row here will be 42 for our total counts. And then we have 29 plus 19. So that's 48. And then we have 15 plus 29, and that's 44. And finally, we have 27 plus 19, and that's 46. So these are our total counts. And then we know our total count for everything is 90 since that's stated up there. And now we can calculate our expected counts. So we can do over, we can do over 25 hours, and we can do under 25 hours. And we can have our gender up here. So we have male and female. And so we calculate all of these. So let me give myself a little bit more room so I can move female a little bit more. I think that should be good. So we can use our formula here. So we have our row column total times our row totals times our column totals. So we can do, and then all that's divided by our total for both. So 44 for our top, so we're taking these two first for our first one. So it's 44 times 42 divided by 90. And that should come out to 20.5. And then we have our female, so we have 44 times 48 divided by 90. And that is around 23.5. And down here we have 46 times 42 divided by 90. And that's around 21.5. And finally we have 46 times 48 divided by 90. And that is 24.5. And so these are our expected values. And now we can calculate our chi-square value. So we have our formula over here. So this is basically observed minus expected. And this is squared divided by our expected. So now we can use that formula to find our chi-square value. So we can write that out. So our chi-square value will be, so we can start from the top. So we have 15 minus 20.5 squared divided by 20.5, and then plus 29 minus 23.5 squared divided by 23.5, and then plus 27 minus 21.5 divided by 21.5, and then finally we have 19 minus 24.5 squared divided by 24.5. And then if we add all of this together, we should get 5.4. And that is our chi-square value. And now that we have our chi-square value, to use the table, we need to first find our degrees of freedom. So our degrees of freedom formula, if you recall, is our row count minus 1 times our column count minus 1. And so we have 2 rows, so it's not the total number of values in each row, but it's the total number of rows. So we have 2 rows minus 1, and then we have 2 columns minus 1, so that's just 1 times 1, which is equal to 1. And then finally we can calculate our p-value, and we can do that by finding so our using our chi-square table. So we have chi-square with our alpha value, or not our alpha value, sorry, our degrees of freedom, which is 1, and we're trying to find the probability that it's greater than the value we calculated, which is 5.4. And we can pull that up on Okay, so we know that our p-value is close to 0.02, and since we're using our significance level of 0.01, we will actually see that this is greater than our significance value, and so we fail to reject our null hypothesis. And so we can conclude that the time spent watching television is independent of whether the viewer is male or female. So now we have our next problem over here. So students may choose between a 3-semester hour physics course without labs and a 4-semester hour course with labs. And the final written examination is the same for each section. And so what we want to do is find a 95% confidence interval for the difference between the average grades for the two courses. So we have our confidence, and it says that our populations are normally distributed with equal variances. So this is really important over here. So we know which formula to use, and if you look at your formula sheet, you'll find this formula on the side for equal variances, and we just need to plug in our values. So first we can mark our values that are here. So we have 12 students for the sample size for our first sample, and then we have 18 students for our second sample, and average for our first sample, so x bar 1 is 84, and standard deviation is S1, so that's 4. And for our second, we have x bar 2 is 77, and our standard deviation is 6. And first we want to calculate our SP value, so we can use this formula over here to do that. And since we want to only find our SP and not the squared value, we can just take the square root of all of this. That's about square root. Here we go. And then we have our N1, so that's 12 minus 1. And then we have S1 squared, so that's 4 squared, plus N2, which is 18 minus 1. And times our S2 squared, so that's 6 squared. And then we divide it all by our sample size for our first sample, 12 plus, and then 18 minus 2. And if we solve this, we should get our answer of 5.305. And then now we can find our t-value. So recall that for our confidence interval, our significance level is 1 minus our value, our percentage divided by 100, so 1 minus 0.95, so that is 0.05, And so now we can find our t with our significance level of 0.05 divided by 2, so that's 0.025. And our degrees of freedom is 12 plus 18 minus 2, and that should be 28. And now we can pull it up on our t-table. So we have our t-table here, and we want to look for 0.025 with our degrees of freedom, which is 28. So that's over here. And if we look, we see that our value should be 2.048. And now that we have all of our values here, we can calculate our confidence interval. So our confidence interval should be x bar 1, so that's 84, minus x bar 2, which is 77, and then plus or minus our t value, so that's 2.048, times our s value, so that's 5.305, and times the square root of 1 divided by n1, so that's 12, plus 1 divided by n2, and that is 18. And we should get 4.05 as our answer, or as our answer for this part. So let me change that. And so we have over here our 84 minus 77. So this is 7. So we have 7 plus or minus 4.05, and that's the same as 7 minus 4.05, so that's our lower bound, and that is 2.95. And then our upper bound is 7 plus 4.05, and that is 11.05. And that is our confidence interval. And so that's in that interval, we're 95% confident that the difference between average grades for the two courses will lie between 2.95 and 11.04. So for our next problem, we have an urban community would like to show the incidence of breast cancer is higher in their area than in a nearby rural area, and we want to conclude using a 0.05 significance level if breast cancer is more prevalent in the urban community. So first we need to write our hypotheses. So we have our null hypothesis, and we're going to have the proportion in our urban area is equal to the proportion in our rural area. And our alternate hypothesis is that the proportion in our urban area is greater than the proportion in our rural area. And we have our level of significance is 0.05. And now we can calculate our p-hat value. So we have our formula off to the side here. You can find it in your formula sheet again. So we have p-hat equals all of our values from our first population and our second population. So we have 20 here plus our second population, so it's 10. So these are the values of the people who have found to have breast cancer, and then divided by our total populations for each sample. So that's 200 plus 150, and this equals 0.085714. And now that we have our p-value, we can solve for our z-value. So we have z over here, and that is equal to our, so we can first mark our values in our problem. So our p1 hat should be 20 divided by 200, and our p2 hat is 10 divided by 150. So we can use those values here, and I'm just going to write it out like that. So we have 20 divided by 200 plus or minus 10 divided by 150 divided by the square root of, so our p-value, which is 0.085714, and we have 1 minus 0.085714, and then times 1 divided by our first sample size, so that's 200 plus 1 divided by 150, which is our second sample size, and all of this is in the square root. And if we solve that, we should get the value 1.102, and so that's our z value. And then finally we can calculate our p-value over here. And our p-value should be p times, and since this is a one-tailed test because we're looking if the proportion for the urban population is greater than the rural population, so we have our probability that z is greater than 1.102, and we can pull this up on our z table. We have our z table here, and then we have 1.10, so this is the closest value, so it's 0.8643, sorry, it's 1 minus 0.8643. This is because if we look back on our table, this is looking at the curve, the area to the left of the curve, but we want the area to the right since we're on the right tail. So we have 1 minus 0.8643, and that is equal to 0.1357. And our p-value is greater than our alpha value, which is 0.05, so we fail to reject our null hypothesis. And that means we don't have significant evidence to conclude that the rural community, that the level of breast cancer is more prevalent in the urban community than the rural community. So we don't have the evidence there. And then for our next problem, we have a study conducted to compare the lengths of time required by men and women to assemble a certain product. And so we have our data over here and its normal distribution. And it says that our variance of times for women is less than that for men, so we know that our variances are unequal. So we need to find, we need to test our hypotheses that the variance is equal for men and women to if the variance is greater than for men than for women. So first, let's write our hypotheses. So we have our null hypothesis over here, and our null hypothesis would be that our variances are equal and our alternate hypothesis is that our first variance is greater than our second variance. And we have our significance level, which is 0.05 since it doesn't specify, and that's what we use by default. And so we have our formula here using our f value, so we can calculate our f value over here by finding our standard deviation squared. So we have our values in our table here, and we just need to square them. So we have, for our first population, which is men, we have 6.1 squared, and then divided by 5.3 squared for women. And our result should be 1.3289. And then our degrees of freedom for men is equal to our sample size of men minus 1, so 11 minus 1 is 10. And our degree of freedom for women is 14 minus 1, which is 13. And now we can use our F table to find our F value at our 0.05 significance level for the value for the degrees of freedom 10 and 13. And we can pull this up on our table. So we have our F distribution over here, and so this is our 0.05, and then this is the degrees of freedom for our first population. So if we look down here, we have 10, and then we can have our 13 over here, And so we have our value is 2.67, so that's our F value. .67, and since our F value is greater than the value, so the F value from our table is greater than the value we calculated, which was 1.3289, that means we fail to reject our null hypothesis. And so we can say that we don't have any evidence that our variance for men is significantly greater than women. And finally, we have our last problem. So this is a different kind of problem. So we have our unbiased estimators here. So we know that theta hat 1 and theta hat 2 are unbiased estimators of theta. And what we want to see is if theta hat 3 is an unbiased estimator for theta. And so we can do that part first. So to do this, we want to, so to determine if a value, if something is an unbiased estimator of something else, we need to see that the expected value of our estimator is equal to the value that we're estimating, essentially. So we can take our equation here. So we have theta hat 3 equals A theta hat 1 plus 1 minus A theta hat 2. And we can take the expected value of all of these. So we have expected value of theta hat 3, which is equal to A times the expected value of theta hat 1 plus 1 minus A times the expected value of theta hat 2. And then we see here that the expected value of theta hat 1 and 2 is equal to theta. So this is equal to A theta plus 1 minus A theta. And then we can rearrange this. So this is theta times A plus 1 minus A, and that is the same thing as theta times 1, which is just theta, since the A's cancel out. And so essentially what we have here is we have proven that our estimator, or that our expected value of theta hat 3 is equal to theta. And so we've shown that theta hat 3 is an unbiased estimator for theta for any number A. And our A isn't even here, so we know that changing our A value won't affect our result. Okay, so now for part B, we have theta hat 1 and theta hat 2, and we say that they're independent, and we want to find a constant A such that the variance of theta hat 3 is minimized. So let's see what we need to do. So we can take our formula again, and we can find the variance of theta hat 3. So we can find the variance of theta hat 3, and that would be equal to a squared times, and then since we have our variances listed here for our theta hat 2 squared, we have sigma squared, sigma 2 squared, plus our 1 minus a squared, and this was 1. So this should be sigma 1 squared, and then this should be sigma 2 squared. So we've solved, so now we can solve for a. So first we want to find, since we want to find the minimized the value of a that minimizes the variance of theta hat 3, that means that we want to find the minimum value. So we can use our derivatives here. So if we find the derivative, we know at the minimum value our derivative will be equal to 0. So we can find dA of our variance of theta 3, and then we can find the derivative here, so that's 2a theta 1 squared plus, or so this would be negative 2a, or negative 2 1 minus a theta 2 squared, and then we're going to set this equal to 0 to find the minimum, and we can divide both sides by 0, so we have just a theta 1 squared minus 1 minus a theta 2 squared equals 0. And now we can distribute this. So we have a why have I been saying theta? It's sigma squared, so it's our variance. Then we have minus sigma 2 squared plus our a sigma 2 squared equals 0. And then we can add that to that side. So we have a sigma 1 squared plus a sigma 2 squared equals sigma 2 squared. And then we can divide both sides. So we can separate our a, so we can write it like this. And then we can divide both sides by sigma 1 squared plus sigma 2 squared. So that would give us a equals sigma 2 squared divided by sigma 1 squared plus sigma 2 squared. And that is our final answer. So that should be the value of a. That minimizes our variance for theta hat 3. And that's all. So I hope this helped, and if you have any questions, feel free to drop by my office hours. Thank you so much. Bye.